Welcome back, everyone. This is lecture number 4, and we begin with chapter number 3. We shall spend 2 lectures on chapter number 3, and we shall be talking about the later books of the elements. Specifically, we will talk about the number theoretical part of the elements, and we shall conclude chapter 3 with the so-called Platonic solids. So before I go on to the introduction of number theory and the later books of elements, I'm going to mention what the consecutive books after the first one that we just talked about, or rather finished the previous lecture, book number 2, 3, 4, 5, and so on, what they were all about. So I'm just going to write rather briefly what was talked about in these books, and then we shall start with the introduction of number theoretical concepts. Okay, so this is lecture 4. Page 1. I hope to finish this in one part, not split it up in 2 parts, as I suspect will not be enough for 2 parts. So let's get on with it. Book number 2 of elements. So this is Euclid and the infinitude of primes. That's the title of chapter 3. Euclid and infinitude of primes, whatever that means. Okay, so book number 2 was all about geometric algebra. Otherwise, book number 2 is about relationships that are easily translated into algebraic equations and frame in geometric terms. So book number 2, rather briefly, is all about geometric algebra. Okay. Things like, for example, a plus b squared equals to a squared plus 2ab plus b squared are actually proved in terms of areas of squares and doubling squares, for example. So much of the book 2 was of this nature, and it was concluded really addressing the quadrature of general polygons and quadrature of general polygons. Okay. Book number 3 had about 37 propositions, and they were all about circles. Positions, and like I said, all about circles. Things like standard results that we know today about chords, tangents, angles, finding centers, circumference of a circle, area, and so on, were all discussed in book 3. Book 4 was all about inscribing and circumscribing certain kinds of geometric figures, for example, circles with triangle, and construction of regular polygons. So let me just write that. Inscribing and circumscribing. Inscribing and circumscribing. Certain kinds excuse me, certain kinds of geometric figures. Also we talk about construction of regular polygons and construction construction of regular polygons. Okay. Book number 5, and I mentioned that in previous lectures, book number 5 was all about the incommensurable magnitudes, or otherwise known as irrational numbers. Incommensurable magnitudes. Or otherwise irrational numbers. Okay. Book number 6, it was all about the similar figures in geometry. Book number 6, all proofs about similar triangles and so on. So, similar figures in geometry. Okay. Books 8 and 9. Well, not 8 and 9, but from 7 to 9 were all about number theory, and that's what we'll be talking about today. Number theory, which is actually the oldest significant development of the subject. It occurred in elements. So that's what we will focus on this lecture, and we shall finish this lecture with one of the latest proposition in one of the latest books, well, at least the 9th book, and that would be the fact that there are infinitely many primes, again, whatever that means. So let me just start talking a little bit about number theory. What is it? Number theory is simply the study of numbers, specifically whole numbers and rational numbers. Okay, so let me just start with some, that's what I'll be talking about today. So I will start with some very simple definitions, and I'll move on. So what do we mean by an even number? Or rather, how did Euclid defined what an even number is? So an even number is a number that is divisible in 2 equal parts. Again, that's the definition of Euclid of an even number. So, definition. An even number is a number divisible into 2 equal parts. Is a number divisible into 2 equal parts. Okay. Examples of even numbers, well, you all know them. 2, 4, 6, 8, and so on. Here's another definition. What did Euclid mean by an odd number? An odd number is a number that is not divisible, cannot be divided in 2 equal parts. So an odd number is a number that is not divisible into 2 equal parts. That is not divisible into 2 equal parts. Okay. Examples: 1, 3, 5, 7, and so on. Okay. What is a prime number? Next definition, that's a definition of a prime number. A prime number is a number that is divisible only by itself and 1. A prime number is a number that is only, I stress the only part, prime number is a number that is only divisible by itself and 1, and 1. For example, 3 is prime, 5 is a prime, 7 is a prime, 8 is not because it's divisible by 2 and 4. 9, although is an odd number, is not a prime because it's divisible by 3. By the way, 2 is also a prime number. In fact, is the only even prime number we have. Every other prime number, it must be odd, but not every odd number is a prime. Example, number 9, and so on. So the next prime after 7, 8 is not, 9 is not, 10 is not, 11 it is, 12 is not, 13 it is, 14 is not, 15 is not, 16 it isn't, 17 it is, and so on. In fact, the further we go down the number line, the harder it is to tell whether a number is actually prime or not. And this is a very deep area of research, actually. Well, not only research, but as I said before, is really hard, really hard to show whether a number is a prime. For example, if you have a number that has more than 10 digits, for example, and it ends in number 1, it's hard to tell whether it's prime or not. In fact, that being a difficult thing is at the heart of the security of computers to date, but that is a completely different story. We're not going to talk about that now. So anyway, so these are prime numbers. 4, 6, 8, 9, 12, 14, 15, 16, and so on are not primes. Okay. Number 1 is neither a prime or composite. But before I talk about number 1, forget this for a moment. I'll move on here. I will continue with definitions. So, definition. All numbers that are not prime are called composite. All numbers that are not prime are called composite numbers. Composite numbers. So, with other words, we are saying that all numbers that are divisible by other numbers other than themselves and 1 are called composite numbers. So these here are composite numbers. So 4, 6, 8, 9, 10, 12, 14, 15, 16, and so on are composite. Because besides themselves and 1, they are also divisible by other things. For example, 4 is divided by 4 and 1 and also 2. 6 is divided by 6 and 1 but also by 2 and 3. Divisors of 8 besides 8 and 1 are also 2 and 4, and so on. So these are examples of composite numbers. Perfect numbers. Well, let me get now to number 1. Number 1 is by convention neither a prime or a composite. Is a special number for sure. Is neither a prime or composite. As just a special number. In fact, is the building block of every other number. In what sense is a building block? Well, number 2 is created by adding 2 ones. Number 3 is created by adding 3 ones. And number n is created by adding n ones. So in that sense, number 1 is a building block of all other whole numbers, natural numbers. And by convention is neither called a prime or composite. Here's another definition. Okay, what are perfect numbers? So perfect numbers are numbers whose, well, are numbers that are equal to the sum of their proper divisors, that are equal to the sum of their proper divisors. Before I move on, what are proper divisors of a number? Proper divisors of a number are all divisors that are not themselves and 1. For example, the proper divisors, forget 1, are divisors that are not themselves, that is. So proper divisors of 6, for example, are 1, 2, and 3. Proper divisors of 4 are 1 and 2. Proper divisors of 8 are 1, 2, and 4, and so on. Okay, so here's an example of a perfect number. So let's see, is 2 a perfect number? Well, the only proper divisor of 2 is number 1, and 2 is not equal to 1. So 2 is not a perfect number. What about number 3? Proper divisors of 3, again, is only 1, so that's out. Proper divisors of 4 are 1 and 2, but 4 is not equal to 1 plus 2. What about 5? Again, proper divisor of 5 is 1, and 5 is not equal to 1. What about 6? Proper divisors of 6 are 1, 2, and 3, and if you add 1 plus 2 plus 3, you actually get 6. So 6 is the first perfect number we have. 6, for example, is equal to 1 plus 2 plus 3. Perfect numbers are very rare, actually. Infinitely many, but very, very rare. For example, the next perfect number we have, I believe, is number 28, because 28 is equal to the sum of its proper divisors. The proper divisors of 28 are 1 for sure, 2 for sure, 4 for sure, so is 7, so is 14, and if you add them all up, you actually get 28. Okay, so some notation. When do we say that a number divides into another? By the way, for the purposes of this chapter, whenever I talk about whole numbers, I mean natural numbers, 1, 2, 3, and so on. So, when do we say that a number divides another? Let's call this another definition. We say that number A, this line means divides into, not divided by. A divides into B. Aside, this is different from saying A divided by B or A divides B. Not the same thing. This means A divides into B in a sense that divides evenly into B if and only if there exists a number C, such that B can be written as A times that number C. In this case, we say that A divides into B evenly. In that sense, divides evenly into B. In this case, A and C are called factors of B, and B is called the product of A and C. Okay, so this definition leads us to one of the most important algorithms, the so-called division algorithm. Division algorithm is nothing other than a fancy way of actually doing long division of numbers, as you know. So first let me write out the division algorithm, and then I'll give an example. So division algorithm. Number m is equal to, so whenever you divide number m by number n, there is this quotient q plus some remainder. This remainder is greater than or equal to 0 or less than or equal to n minus 1. So when n is divided into m, you have the quotient q and possibly a remainder r. Whenever, and the remainder, the possibilities for remainder are from 0 to n minus 1. When there is no remainder 0, in that case you get back to this definition. In this case you say, so if the remainder is 0, you say that n divides evenly into m, and so does q. But if there is a remainder, then there is a remainder. For example, let's see, 17, this is what you do with long division. 17 divided by 5. 5 goes into 17 3 times. So 5 times 3 is 15. 7 minus 5 is 2. You have a remainder of 2. Okay, the most that the remainder can be is n minus 1. In this case, 17 is your m, your n is 5, your q is 3, and your r is 2. So this is your long division, this is how you do the long division, but in fancier terms you write 17 as 3 times 5 plus 2. So 5 goes into 17 3 times with a remainder of 2. And if you add them all up, you actually get the number. So whenever we refer from this point on to long division, we will talk about division algorithm, not the long division. Okay, so division algorithm is actually used and reused a lot in the so-called Euclidean algorithm. What is Euclidean algorithm? So before I talk about Euclidean algorithm, you are all familiar with the concept of the greatest common divisor between two numbers. So what is the greatest common divisor? As the term explains itself, is the largest factor that goes into two numbers at the same time. For example, a notation for that is GCD. This means the greatest common divisor. Greatest common divisor. For example, what is the GCD between 3, the greatest common divisor of 3 and 5? The only factor that 3 and 5 have in common is number 1. So the GCD is 1. Okay, what about the GCD of, let's say, 14 and 28? Well, okay. Is 2 a common divisor of 14 and 28? Meaning, are 14 and 28 both divisible by 2? The answer is yes. But is that the largest common divisor? No. The largest common divisor would be actually 7. 7 divides into 14, 7 divides into 28, and that's the largest. 7. Well, so if the GCD between two numbers A and B is equal to 1, A and B are called coprime. Coprime. It doesn't mean that number A and B in themselves are prime numbers. No, not necessarily. But if the greatest common divisor between two numbers is actually 1, then the numbers are called coprime. For example, 8 and 9. The GCD between 8 and 9 is actually what? It's 1, yet neither of them is actually a prime number. But 8 and 9 in relation to one another are called coprime because they have no other common factors besides 1. Okay, so given any two numbers in general is not so easy to find the greatest common divisor. These are very simple examples because we are very familiar with these rather small numbers, but in general, if you're dealing with or if you want to find the GCD between two large numbers, then just contemplating which number goes into which number and what is the largest is not a good way to go about it. So in this case we have the so-called Euclidean algorithm. Euclidean algorithm is nothing other than a repetition of the division algorithm, and it helps you find the greatest common divisor between two numbers. So I'm not going to write a formal definition of the Euclidean algorithm. I just want to show you how to use it to find the GCD between two numbers. So I'm going to explain the Euclidean algorithm with an actual example. So Euclidean algorithm. Let's say that I want to find the GCD between, I don't know, let's see, number 270 and 192. Can you do by trial and error? Sure, but it does take some time. So let's see, here's what you do. Given any two numbers, one of them certainly has to be less than the other, because it makes no sense to talk about two identical numbers and finding their GCD. So given any two numbers, one certainly has to be less than the other. In this case, 192 is less than 270. So the first step is to divide 192 into 270 and write it in terms of the division algorithm. What does that mean? So you are going to take, you can perform this aside. So 270 divided by 192. Well, 192 goes into 270 certainly once. So 192. 10 minus 2 is 8. This is 16 minus 9 is 7. Okay, so we're writing 270 as 192 times 1 plus 78. Okay, so I'm not going to write that as the long division, but I'm going to write that first step in terms of the division algorithm, as in here. Okay, so I have a remainder. The remainder is 78 and surely is less than 192. Now, to proceed in the next step, be careful. What you want to do now is look at these two numbers, 192 and 78. Not this quotient. You're not going to look into this one. As far as this step is concerned, you are going to forget about that number. You do nothing with that number for the moment. Okay, so you look at the n, at the number n, the number that you wanted originally to divide into 270. So you have 192 and you have the remainder 78. Obviously, the remainder 78 is less than 192. So what you do is you perform the division algorithm once again with these two numbers now. So you are going to divide 192 by 78 and then see what you get. So let me just do this here. 192 divided by 78. 78, I think, goes into 192 twice. So 8 times 2 is 16. 7 times 2 is 14. Plus 1 is 15. So I believe this is 36. So now you write 192, 78 times 2 times the quotient plus the remainder 36. Okay, well, we divided 192 by 78. 2, I repeat, is the quotient. In this step, you're going to leave the 2 alone, and then you are going to repeat the division algorithm now with these two numbers, 78 and 36. Obviously, 36 is less than 78, so we are going to divide 36 by 78 and see if there is a remainder. So 36, let's see, 78 divided by 36. I think 36 goes into 78 twice. 6 times 2 is 12. 3 times 2 is 6, plus 1, 7. You have a remainder of 6. So you have 36 times 2 plus 6. Again, forget the quotient here. You have these two numbers, 36 and 6. 6 is less than 36. You perform this again. So you have 36 is equal to 6 times 6 plus 0. There is no remainder because 6 times 6 is 36, and that's where the process stops. That's where the algorithm stops. Okay, so what does it tell us? In this column here, you will be looking for the last non-zero remainder. The last non-zero remainder is this. The last non-zero remainder would be the GCD between these two original numbers. So in this case is 6. So this is the GCD. This is the GCD. I'll move on to the next page. Euclidean algorithm, actually the statement of it. So, lecture 4. Second page. Give me a second until I write the borders again. Okay, at some point we will talk about the reversed Euclidean algorithm, but certainly not today. And what is that good for? It's actually a very important and common tool in general in number theory. Okay, so the GCD between these two numbers is actually 6. Moving on. There is a corollary to the Euclidean algorithm. I can write that in general terms. So this is corollary to Euclidean algorithm. Okay. So for every pair of integers a and b, for every pair of integers a and b, there exist integers x and y such that a times x plus b times y equals the GCD, equals to GCD of a and b. This is a very important tool. Again, this corollary tells you that there exist numbers given any two integers a and b, whatever their GCD is, there are integers x and y such that this whole thing is true. However, this corollary, it does not tell you how to find x and y. And this in general is very, very difficult. Again, I'm going back to the security of computers because this does play, actually this concept does play an important role. Finding x and y is surely not easy at all. But for you know, when the GCD between the two numbers is actually equal to 1, then one can actually use the so-called extended Euclidean algorithm, which I will leave alone for the moment. In particular, as I mentioned before, ax plus by is equal to 1 in case of coprime numbers, coprime pairs, because their GCD is 1. That's what you call coprime, as I mentioned before. Okay, so I will move on to the next proposition. This is proposition 31 in book 8. So, proposition 731. It says that every, and these are important ones, the ones that I'm mentioning, and well, some will be without proof, but the ones that I'm proving are rather important. So proposition 731 says the following, that every positive integer greater than 1 is either a prime or a product of primes. Let's see. Every positive integer greater than 1 is either a prime or a product of primes. Okay, before I go into the proof of this, the statement is saying, among other things, the following: the flavor of positive integers are 2. Given any positive integer, that number is either a prime or not. To say that a number is not prime, it means is composite. It means that it has other factors besides itself and 1. But we're saying a little bit more here. We're saying that if a number is actually not prime, therefore composite, it must be then a product of primes. So the flavors are 2. A number is either a prime, and if it's not, most definitely can be written as a product of primes. So I'll write the proof. So let n be any arbitrary positive, any positive integer greater than 1. Okay, greater than 1. That is not a prime, because if it's a prime, then we're done. There's nothing to talk about. That is not a prime. That's the interesting case. Again, as I mentioned before, pick anything, any number, it's either a prime or not. If it's a prime, nothing to prove. Now we want to show that if it's not a prime, it's a product of primes. That's the point. So we have an integer that is not a prime. If it's not a prime, as I said before, then it must be composite, meaning it must have other factors other than itself and 1. So in that case, you should be able to write the number n as the product of its factors. So let's say then, n must be equal to a times b. By the way, there is no special reason why I'm just writing these 2 factors. A number can be product of 2 or more factors, but the line of reasoning is exactly the same, so it makes no sense to consider 3 or more factors. So if a number is not a prime, then it must have some factors. Let's call them a and b for sake of simplicity. Now, since they are factors of n, they cannot possibly be greater than n. They have to be less than n. So we write where a and b are less than n. All factors of a number are less than the number itself. Factors of 6, for example, are 2 and 3, because 6 can be written as 2 times 3, but both 2 and 3 are less than 6. That's what we're saying here in general terms. So we look at A and B. So we look at A and B. So what are the possibilities for A and B? A and B are primes or not, are both prime or they are not. If A and B are both prime, then we are done. Why are we done? Because we are writing n as the product of two primes. So let's see what happens when A and B are not prime. Let me write this. A and B are either both primes or not. If they are both prime, then we are done. We are done since we are writing n as product of primes. So this case is not interesting. So if they're both prime, we're done. What happens if either of them is not? So we consider that case. If either A or B are not prime, if either A or B are not prime, primes, then they can be factored. Then it can be factored. Into smaller positive integers, each greater than 1. Can be factored into smaller positive integers each smaller than 1. So if we continue in this matter, so let me just do this aside for a little bit before I write. So we said n is equal to A times B. A and B are not prime. If A and B are not prime, then each of them can be factored into smaller factors. So let's say A can be factored into A1 times A2 times, and B can be factored into B1, B2. A1 and A2 are less than A, B1 and B2 are less than B, and we look now at these 4 factors. What are the choices for them? Well, they either prime or not. If they are prime, we're done because we're writing n as a product of a bunch of primes. But if they are not, then we keep factoring each of those. And each time we come up with factors that are smaller than the previous ones, but always greater than 1. So we continue this process basically. So if we continue in this matter with each of the factors, let me write this down. If we continue in this manner with each of the factors, Since the factors are getting smaller and smaller each time, you get smaller and smaller factors. Since the factors are getting smaller, after a finite, so you cannot really do this infinitely many times. There has to be a point where it all stops, because you're going smaller and smaller and smaller each time, and there are finitely many such factors. So and that's the key, after a finite number of steps, we'll find a factorization of n where all factors are prime, because the primes are the ones that you cannot break them down further. So whatever you left with at the end, they all will be prime factors, because these will be the ones that you cannot break any further. So what you'll be left with is just a bunch of primes. So after a finite number of steps, we'll find a factorization. We'll find a factorization of n where all factors are prime. Where all factors are prime. And then we're done with this proof. Okay, so I will write two more propositions. Probably I'll prove one of them, and then we'll move on to the final big theorem for this lecture. It's not very long, and it has to do with primes being infinitely many. So meanwhile, I'm writing these propositions because I will mention them in further proofs. So the next one that I want to bring about is proposition from the 9th book, proposition 14 from the 9th book. It says the following: a composite number can uniquely be factored into primes. Well, that's not the original statement, so I'm just going to write the original statement, but that's basically what it means. So if a number be the list that is measured by prime numbers, again, sounds a bit weird, but it means nothing other than what I said a second ago. So if a number be the list that is measured by prime numbers, it will not be measured by any other prime number. It will not be measured by any other prime number. Okay, I'll explain with an example. With other words, this means that a composite number can uniquely, I'm stressing on uniquely, can uniquely be factored into primes. Okay. So let me just take number 15. Number 15 is a composite number because besides 15 and 1, it has what other factors? The other factors are 3 and 5. As you can see, both of them are prime numbers. So what this theorem is saying is as follows. You cannot find two other prime numbers that are different from 3 and 5 such that when you multiply them together you get 15. Of course, 15 equals to 5 times 3 is the same as 15 equals to 3 times 5. So when we talk about uniquely here, we don't mean the order in which the factors are listed. By uniquely, we mean finding something else that is not 3 and something else that is not 5, but prime, such that when you multiply them together, you get 15. That's what we mean by the unique part. This is one of the fundamental concepts of number theory as well. Okay, I'm not going to prove it, but I shall use it later. All right, another proposition of interest is proposition 30 in book 7, actually. So proposition, I'm going a little bit backwards, but it's okay. Proposition, proposition 7, 30. It says the following. If P is a prime number and divides a product, A times B, then either divides A or divides B. So, if P is prime and P divides A times B, then either P divides evenly into A or P divides evenly into B, or P divides A or P divides B. When I say divide in this case, I mean evenly, no remainder. Alright, so here's a proof. Here's a proof of that. Let P, so if P is a prime, that means that we are given some arbitrary prime number P. So let P be some prime number. B prime. And it is given that P divides A times B. But let's say that P does not divide A. We have to show that P must divide B. The argument, the reverse argument, works the same. So we have P being a prime number. We know for sure that P divides this product but does not divide A. We must prove that it divides B. That's what it means to prove that either divides A or divides B. Same works with saying that P divides B, but P divides A, but not B. Okay, so this means P does not divide into A. We must show that P must divide B, and then we're done. Okay, since P, it is given to divide A times B, then there must exist some number, C, such that one of the earlier propositions or definitions that I wrote in page 1, to say that a number divides into the other, it means that you can write this number as this number times another factor. I'm calling that other factor C. So there must exist a C such that P times C equals A times B. That means that P divides into this, whatever this is. It means that there is some other number C such that when you multiply them together you get this other product. Okay. Also, since we assuming that P does not divide A, then GCD of P and A must be what? Must be equal to 1. If P does not divide A, it means that they have no common factors. And if they have no common factors, it means that the greatest common divisor is 1, or their GCD is 1, or they are coprime. So by proposition 31, by corollary to the Euclidean algorithm, then by the previous corollary, there exist integers x and y, x and y, x and y integers. That means element of the set of integers, such that what? Such that P, their GCD is 1. So there must exist x and y integers, like in here, such that P times x plus A times y must be equal to 1. Okay? So far so good. Now, we all know that B, number B, whatever number B is the same as writing B times 1, because every number has as factors itself and 1, meaning you can write it as a product of itself and 1. So now, instead of this number 1, I'm going to write whatever number 1 is equal to. So B times this number 1 can also be written as px plus ay. Okay, so that means that B on this left hand side is equal to bpx plus bay, right? Well, okay. BA or AB from here, I know is equal to P times C, no? A times B is equal to P times C. So I'm going to substitute this AB by PC. So continue here. B is equal to BPX plus, instead of BA, I will write PC. PCY. Okay. So on the right hand side though, I can do what? I can factor out what? I can factor out P. So if I factor out P, I get BX plus CY. Well, what does that mean? B is an integer, X is an integer, C is an integer, Y is an integer. Multiply them together, add them together, you get some other integer. So at the end of the day, you're saying B is equal to P times some other factor. That means that P divides into B evenly. So this means that P divides B. And that's exactly what we wanted to show. All right, so now comes the big theorem for this chapter. And this is Euclid's proof of infinitude of primes. So I'm just going to write them in a separate paper. It's not very long. Let's see. Okay, I do the usual. Mark the borders. page 3. So here's the theorem. And this one is due to Euclid himself. And the statement is, there are infinitely many primes. Is one of the most beautiful proofs in mathematics, for the very fact that is easy to understand and it is accessible for any non-expert in the field, and one can simply use the notions that we have just mentioned in this lecture. Okay, so first of all, before we talk about this proof, why should we actually be concerned with primes being infinitely many? You may say, well, do we really need them to be infinitely many? Meaning, can I use finitely many primes and create infinitely many composite numbers? For example, a number 5 is a prime. 5 times 5 is 25. I created a number simply by raising 5 to the power 2. If I raise 5 to the power 3,